goes in here, so I got gamma 1, and similarly I can calculate gamma 2. So for each of these values calculated out of the appropriate form of modified Rolle's law, I can get calculated values of gamma 1 and gamma 2. And I could do the same thing over here for constant pressure data. The data that are given in the database are these three columns of data, x1, y1, and t, across the composition range. And I could do the same thing, use the same equation to calculate the gamma, so I can have a column for gamma 1 and gamma 2. Everyone clear about that? It's pretty straightforward. Well, let's look at some data. I think I have here some examples. Here's an example of the vinyl acetate. This is out of some database. This is system number 653 in this particular database. And these are data shown for vinyl acetate and 2,4-dimethylpentane. And as I said, this is a constant pressure data system. This is all at 1 atmosphere. And here are my x1, y1 values and the corresponding temperatures. Now, if we're going to be able to analyze these, we need to be given the Antoine's equations for the two components. Because we recall here, we need that to be able to calculate at the different temperatures what this the appropriate vapor pressure is. In this case, it would be P1S. So here's the Antoine equation for this particular database, and the constants for the two components are given here. Okay. So now, using that method that I showed you before, just for calculating point by point what the activity coefficients are, I can do that and then plot them up. Let's take a look here at what that looks like. Everyone see that? So I've got gamma 1 and gamma 2 plotted up here. And you notice that the limiting values, that at a mole fraction of 1, the activity coefficient has to go to 1. We require that. So gamma 1 goes to 1 here when x1 goes to 1. Gamma 2 will go to 1 when x1 goes to 0, or x2 equals 1. Right, so let's make a note of that fact. And gamma 2 goes to 1 as x2 goes to 1. So when the mole fraction goes to 1, the respective activity coefficients go to 1. At the other end, we will identify here, you usually have to extrapolate limiting activity coefficients, and we'll designate them in this way. This is gamma 2 infinity, gamma 1 infinity. When we look at this set of data, and the activity coefficients that come out of them, we've got obviously positive deviations from ideality, but to the eye it isn't immediately evident whether we have an azeotrope or not. If we examine the table, we'll be able to pick that out, but if I look at a plot of these data, then it looks like this, so it's obvious that we've got a minimum boiling azeotrope for this particular case. And here's just a plot of all of those points.
And why is it considered a positive deviation? Is it because the dew point temperature isn't equal to the bubble point temperature, it's higher? Is that why it's considered?
See, the way I defined it initially was in terms of pressures. So I said the bubble point pressure was higher than Rolle's law value if we have positive deviations. So the opposite is going to be true of temperatures.
Okay, and so clearly the bubble point temperature is lower than a straight line, so,
Right.
or than
And
the line it would be.
It's not even a straight line here, but
Yeah, the line it would
line
be.
would look curved, but above
Yeah.
these.
Okay.
Yeah. Okay. So this is where we are, so you can see that we've got access to these activity coefficients, and we can consider what we might be able to do with them. Let's look at another system This is one that exhibits negative deviations, and that's the water formic acid system. So here again, at the pressure at 1 atmosphere, 760 millimeters of mercury, I've got X1, Y1 values, T's for each of these. Calculate the vapor pressures in the spreadsheet, and thereby calculate the activity coefficients. And you can see that they are all less than 1. Limiting values here are shown. This would be an illustration of gamma 1 infinity. We would have to extrapolate to get that. It would be gamma 2 infinity, which we could extrapolate to. And when we plot that up, it looks like this. So it would be that this is all pretty clear. Now it's common for us to actually, instead of plotting the activity coefficients themselves, to plot their logarithms. And we'll see why that's convenient, but in any case now you can see you can certainly do that. And the logarithms of numbers greater than 1 are going to be positive. The log of numbers less than 1 are going to be negative. And so we're not surprised to see these look like this. This is a replot of the same data now, but as logarithms. So the limiting values here are going to be 0 in each case as the mole fractions, or respective mole fractions, go to 1. And then I'll have limiting values here for the logs of these activity coefficients if I extrapolate to a 0 mole fraction for them. So it's important that you understand this limiting behavior.
Are we going to learn why? Oh, you said we're going to learn why that's important later? Because why the reformulation is important later?
Yeah.
Okay.
In fact, I think we can see that right now. And that is the correlation of activity coefficient data using the Gibbs-Duhem equation. And the idea here is that what I said before is that there is a relationship between gamma 1 and gamma 2. They're not just willy-nilly. You can't write one function and then another function. They must relate to one another in a certain way. And one of the things that I said, one of the outcomes of that fact is that if the activity coefficients are greater than, if the gamma 1 is greater than 1, so will gamma 2 be greater than 1. And likewise if they're less than 1. So let's take a look at this. The Gibbs-Duhem equation is going to be this relationship between the gammas that I'm going to derive. And the way we derive that, so this is what I'm going to do right now, is to write down two equivalent expressions for dg. Both of them completely general. Okay. This is now for an open system. So that's a completely general expression. But I also know that I can express any extensive property in terms of the partial molar properties. So I know also that G can be written as either the summation of Ni times the partial molar properties. And if I differentiate that, which is just true in general, I'm going to get summation of Ni d mu I plus summation of mu I d Ni. Now what I know is that these are both true. So if that's the case, then that means a certain clump of terms are going to have to be 0. So this implies minus SDT plus VDP minus summation here Ni d mu I must be equal to 0. So let's look at constant temperature and pressure binary system. I'm making an approximation here because If I fix both the temperature and the pressure, I'm over conditioning the system. But this can be done to a reasonable approximation, so I'm gonna make that approximation, and that will get rid of these two terms. And if it's a binary system, what I end up with is the statement that, look at 1 mole, is the statement that x1 d mu 1 plus x2 d mu 2 is equal to 0. So you can see where I'm going with this. Mu 1 can be written out as mu 1 0 plus RT log gamma 1 x1. And similarly, I'll do it here, mu 2 write that out. So if I want to write d mu's here, so if I now write them all together here to write the summation equating it equal to 0, I'm going to end up with well, I can certainly get rid of the RT, but what I notice here that x1 d log x1 is x1 dx1 over x1, or just dx1. Similarly, this is just dx2. I'll note here that, see how much room I got, save it a little bit, so dx1 plus dx2, of course, is equal to 0 because x1 plus x2 equals 1. So these go out. And what I'm left with is the following. This is the Gibbs-Duhem equation. And it's for a binary system at constant temperature and pressure. The completely general Gibbs-Duhem equation is this guy. But here you see in the form of a differential equation, we have a relationship between gamma 1 and gamma 2. And I need to know the value at some point for, if I'm going to integrate this, I need to know the value, absolute value of gamma 1 or gamma 2 at some point, and I've got that. Because I know that gamma 1 is equal to 1 when x1 is 1, and I know that gamma 2 is equal to 1 when x2 equal 1. So I'm in good shape for integrating this equation. And we're close to running out of time, so I just want to discuss this a little bit more, what we can do with this. One of the things we can do is when we've got a vapor-liquid equilibrium data set, and many of them are in the literature, you can check the internal consistency of that data set by whether or not the data obey the Gibbs-Duhem equation. So these are what are called internal consistency tests, and a number of the old databases were found to be internally inconsistent and had to be thrown out. But the more important use for the Gibbs-Duhem equation is that if we have knowledge of one of the activity coefficients of the composition, we can derive the other one. And that's the first thing I'm going to show then tomorrow, about how we can do that. So that's it for today. Let me collect any unclaimed homework. First of all, everybody get a chance at